So, in this class we will start to discuss about beta cleavage reactions. So far we were dealing about the alpha cleavage. So, we will start dealing with beta cleavage reactions. As we have in the case of carbonyl compounds, like if you have a carbonyl compounds in which your C alpha and C beta bond are weak, okay, that type of carbonyl system can undergo a beta cleavage reactions. I will just draw a structure so that you will. So, this is acetyl cyclopropane, right. If you have a system like this, and if you see the system, you can see this is your alpha and this can be your beta, this is C alpha and C beta bond, or you can write this alpha and beta. Since the system is symmetrical, okay, there is no need to worry about that part. So, if and you know that because of your ring strain, okay, this alpha beta bond is weak. Okay. So, if you have this type of systems, then you can see beta cleavage reactions taking place. Okay. So, a carbonyl system where you have C alpha and C beta bond weaker, okay, in that time when you excite the carbonyl, you will get chemistry from beta cleavage reactions. Okay. Now, we will take the same example and see how the chemistry work. I have taken my acetyl cyclopropane, I have shining light H mu. So, what happens? As you know that this carbonyl gets excited, okay, to its singlet S1, and there are cases where it can undergo intersystem crossing to triplet. See, in case of this type of system, you can see chemistry happening both from your singlet as well as triplet. Okay. It is not that predominantly it happens from triplet, you can get some cases from singlet also. Okay. How this chemistry happens? Basically, once your carbonyl gets excited, okay, now the carbonyl is in the singlet state as well as in triplet state, it has an excited energy. Okay. This excited energy is then transferred to your C alpha and C beta bond, and that is how the alpha beta bond gets cleaved. Okay. So, it is a type of an energy transfer taking from your excited ketone to your C alpha and C beta bond, which makes the chemistry to occur. So, once I have now triplet state, I can say that it can happen from S1 as well as T1, okay, depends upon your ketone, okay, to give me what? I can cleave this bond, okay. This is my beta and alpha bond. What I should get? I should get, if I break this, so I get this. Okay. So, what is this? This is your 1,3 diradical. Fine. So, this is your photochemical process, actually seeing means this is your primary photochemical process. Then what happens? Then you see your what this radical chemistry happens. See, till now the photochemistry happens. Okay. After that, as we said, what is going to happen to my radical then. So, what we can, what this 1,3 diradical does, because we have studied about 1,3 diradical, what it can do. 1,3 diradicals, we have studied 1,5 diradicals, we have studied 1,4, we have studied 1,3 diradicals. Okay. So, what this 1,3 diradical does? It cannot do a recombination or cyclization again to give back your cyclopropane, because that is a ring strained one, or what it can do, which you have studied, like, yeah, now it can do your 1,2 hydrogen shift, that is you normally see. Okay. This hydrogen can be shifted, it is a radical. Okay. So, you can do a 1,2 hydrogen shift. See, the idea is that you should know what this radical, simple it is, what 1,5 diradical does, what 1,4, what 1,3, you should know these 3 radicals. Then you are, most of the time you are, once you know the photochemical, then you are anyhow you are going to generate your radical, then just by radical knowledge you can do this chemistry. Okay, if I shift this hydrogen, just a 1,2, I call this as an A, then I will get a product like CH3, CH double bond, CH, I will get a product like this, right. So, I can call this A. I can also shift my hydrogen like this also, no? Okay, it is, sorry, it is radical. I can shift like this also. If I shift in that case, then I will get CH2 double bond CH, so I can think of getting 2 products now just by 1,2 hydrogen shift. So, I know the idea of 1,3 diradical. If it is a 1,3 diradical, I will be most of the time going for hydrogen shifts. So, just I have to see how this hydrogen shifts. There are 2 possibility, A and B. Okay. So, I get an type of alkene which is internal, I get an alkene which is terminal. So, you know internal alkenes are favored, right. So, I can say this is your major product and this will be your minor one. Clear? So, this is the simplest example, okay, to do this chemistry. Now, we will take some more examples and we will see how this works, or we are sure with our radical chemistry. We will take our second example. You can take an example like this. Okay. Now, we will see this ketone how it works. So, as I said, once I photolyze, it goes to S1, then you can get to intersystem crossing to T1. Both the chemistry, photochemistry can happen from the both the states. Just for it can happen predominantly from S1 and T1. So, you can then get your beta cleavage. So, what beta cleavage I am looking for here? So, which is the weakest bond? Carbon oxygen. So, this will be your weakest bond. So, I can break this bond, right? Yes or no? See, you have a ring strain. Okay, you want to break a CC bond or you want to break a CO bond? CO bond. So, I am just breaking my CO bond. So, it is a typical epoxy ketone. No? So, I can get this type of radical now, ketone with this type of system. So, what we call this again? See, sorry, in this case for just a minute, in case of epoxy ketone, okay, you never get your intersystem crossing to triplet, just that is, this step never happens in the case of epoxy ketone. If it is a cyclopropane system, yes, you can see intersystem crossing, but in the case of epoxy ketone, your singlet state dominates the chemistry. So, you see always your chemistry happening from S1, not from your T1, fine. So, you just cross this. So, this is not going to happen in the case of epoxy ketone. So, whatever I am getting, I should get from my S1 state. Yeah, the chemistry is same, it is N pi star, okay, S1 N pi star chemistry. Again it is a 1,3 diradical. Yes. So, what now this 1,3 diradical can do? What this 1,3 diradical can do now? Huh? Is there is any hydrogen I can figure out here? See, this is my radical, right, 1, 2, 3. I do not have hydrogen here. Then it does a 1,3 1,2 methyl shift. Instead of hydrogen shift, I can do my methyl shift. So, it can do 1,2 yes. If I do 1,2 methyl shift, so I can shift this methyl. Okay. So, I get a diketone type of system. Any doubt in this example? So, you are basically I have taken one example where I dealt with cyclopropane system. Now, I am taking an example I am dealing with epoxy ketone system, and I said in cyclopropane system the photochemistry can work from S1 as well as T1, but in epoxy ketone system it works mostly from your S1 state. But in both of the case you are getting 1,3 diradical. In one case you are shifting your hydrogen, in another case you are shifting your methyl, that is all. So, these are the two main things you can see in beta cleavage. So, based on this we will do now n number of examples. Clear? We will do some examples based on this knowledge. This is the two broad class of ketones which does beta cleavage reactions. So, I have a system like this now. Okay. So, what you say, this is a example of your cyclopropane, right, the class of ketone having a cyclopropane. So, then what you say how the photochemistry can work, you will say that it goes to S1, it can undergo an intersystem crossing to give my T1, and the chemistry can happen from both my excited states. So, to give me a bond cleavage. So, I want to break my bond. So, this is alpha and this will be beta. So, can I cleave here? So, I can cleave this. get a 1,3 diradical. Now think what you can do with this 1,3 diradical. Can you write by yourself what this 1,3 diradical can do? Sorry, I have missed my aromatic. Just a minute, I have missed my aromatic in the earlier case. Sorry. It's a type of an aromatic system. Okay. What this molecule can do now? Write like all the products, like what you can think, and say me which will be the major and minor. You can think about. So I can put my hydrogen here. Okay. So I can write two products now. Yes, I can write a product moving this hydrogen here, or I can write a product moving this hydrogen to this 1,2 hydrogen shift. I can do in both the ways. So if I move my I can call this A, or I can move and call this as B. I can do like this, then I will get a, if I move my hydrogen in this direction, then I can get an alkene like this. Yes, other way around, can I have a system where you can get your alkene like this. So we can get two products right now. So which you think like can be more or major? Yeah, I can call this as A, I can call this as B, because you know that alkenes internally is much more stable. Fine, that's good.
Hydrogen can be extracted from CH2.
Hydrogen can be
CH2 from the pentane ring.
CH2. CH2, which CH2 you are talking about? This hydrogen.
Pentane ring.
This hydrogen.
Yes, sir.
You want to abstract this hydrogen for what?
The conjugation is extended to both rings.
No, it doesn't happen from here most of the time, because it is just your alpha beta, na? Your first photochemical process. You are getting only 1,3 diradical. Why you want to move your 1,3 diradical here?
Yes, sir. That outside free radical is not, I think it's not very far from the CH2 carbon.
You want to abstract this hydrogen.
So I think so it is.
Okay, fine. You want to take this radical and abstract this one.
Yes, sir.
Then what you want to do? You want to create an alkene. How? See, you want to have a other radical is there in the system, right?
The terminal radical can abstract the hydrogen.
You want to abstract this hydrogen and make it this one.
Yes.
You think it is possible? It has to bend down. Okay. In this case, it never does. Whatever you are thinking is fine. You can take this hydrogen here and then you can generate an alkene. That is also possible. But in this case, it does not happen. Okay. Yeah, radical chemistry, when you are writing radical chemistry, that is why I said write all your products. Okay. Nothing wrong in it. So I have a system like this now. Okay. What it can do? So once I fertilize, again I said that you know all these things, that it gives S1, then inter-system, then gives you T1, fine. Then depending upon your molecule, it can get from your S1 to T1. So, I can write here a system of what? I can call this alpha beta, right? So, can I cleave this? You can get this, fine. So, from this I can write two products. You have an hydrogen here, okay. I can shift it this direction, okay, to get an in like this. See, first we will write all these products, then we will decide like which will be formed more or not. Get an alkene like this, or I should get a system nice alpha beta E0. Now you know that among this which will be formed, we can call this A and call this B. You can clearly say B will be formed as the major product. Now, if you think this chemistry little bit carefully, I have another chance of cleaving my bond. Na? You see, I have cleaved alpha beta. If I cleave this one, what happens? This is also an alpha beta bond. This one, this particular, that also be an alpha beta bond. As I say, this is alpha beta, this also an alpha beta. In previous case, it was so symmetry that if you break on both the sides, it is same, but in this case, it is different. Okay. If I break this one now, then what happens? Okay, if I break from here, what I should get? Can you write? I can get like this, yes or no? See, that is why I said, see, if you have different examples will tell you many ideas, like it is not only you have to look for one alpha beta bond, there is another alpha beta bond also, okay. So, you have to do that chemistry also. So, you get a system like this, now you have an hydrogen. So, what it can give? Again I can think of two products, because again it is a 1,3 diradical, like this is 1,3 diradical, again I can call this also 1,3 diradical. So, I can write two products now, one I can shift my hydrogen here, okay, to get a right. So, I have taken a simple chemistry now, like I have taken a ketone system with a cyclopropane, and I am saying that, see, you can get now 4 products A, B, C, and you can get D. Okay. So, these are all plausible products. Okay. Then once you go to lab and you do the reaction, then you know which will be formed major. See, if you see from here, I can say B, C, D can be formed, okay, without any problem. Yes. Okay. So, that is how you should know how this, see, the chemistry, photochemistry here is very simple, just it goes by S1, then intersystem cross to T1 to give me a 1,3 diradical. Then what I am going to do with this 1,3 diradical? That is how where the chemistry starts. I say 1,3 diradicals, now you know it is does hydrogen shift nicely. So, you have to do in both the possible ways, because you will get a 2 radicals 1,3 diradicals and your hydrogen will be in the middle. So, you have to do in both the ways. Then the care should be taken that if you have other alpha beta bonds, then you should involve that also. Clear? Now, we will take one more another example. Guys should think about. Just like previous case, I have taken, if you compare this example with the previous example, okay, it is just like the similar system, but I have like methyl substituted here and there. So, you should understand why I have what will do, what this methyl has some influence or not. Okay. So, once it is, then you are fine, you do your first step, that is S1 to T, right. So, I can call this alpha beta, okay, and I am breaking down this one. I get a radical, I can get a radical, no sorry, I can get a radical here, I can get a radical here. Yes, then I have an hydrogen here. So, you can write two products, then you can see first initially you try to write all the products, that is where, then decide, then understand which will be the good one. So, you can get nice here. If I move this hydrogen across here, I can get one product like this, yes, or I can think of getting another product where I have an alkene outside. Yeah, right. If I move this hydrogen this to my cycloprop, like my secondary isopropyl unit, then I will get a system like this. Or if I move my hydrogen here, then I will get an system with an alkene outside with a double. So, from this structure itself you can clearly say that which you want to. So, it looks like B to be formed in major, right. Now, you have another question you have to ask yourself. I have another alpha beta bond here, can I break this? Whether the molecule tries to break this alpha beta bond. Previous case I have broken this bond, I have wrote a cyclohexanone type of system, cycloheptanone type of system. In this case, can I break this? Just try and see what you get, why you should not break. If I break this bond, okay, what I should get? I get a radical here, I can get a radical here with my so why you do not want to break this? No hydrogen is there, so you do not want to break this, that is the criteria. Yes, right. Okay. So, I cannot write any other product. So, based on this, that is why the molecule says I am not going that side. Now, this molecule can do any other chemistry. Huh? No, I am talking about photochemistry. Any other photo reactions can this molecule do? See, that is what, because in this class we are just thinking about beta cleavage, okay, we just our eyes goes only on beta cleavage. Why this molecule do alpha cleavage? See, I just made this molecule so nice that it has a methyl there, okay. So, that whatever radical is formed, that radical can get stabilized. So, why cannot this molecule do Now alpha cleavage reaction, it can do pretty well alpha cleavage. Okay. That is why you put a methyl there. So, there are reactions where you have to compete your alpha and beta cleavage. It is not that you see today I am taking a class where I am taking only beta cleavage. So, I am taking only beta cleavage example, okay. But molecule does not do like that. Okay. So, whatever favors it does alpha cleavage as well as it does beta cleavage. So, if then so I can do an alpha cleavage here, because I know that I cannot do an alpha cleavage in that direction. I can do an alpha cleavage here because I get a stable. I get a system like this, okay. And you know pretty well what this does. It can abstract an hydrogen to give me an aldehyde, right. That is what we studied in alpha cleavage reaction. Then you can say it can decarboxylation, all this process can happen, but you should know, yes, this also undergoes a alpha cleavage reaction. So, I leave you with this radical. You can do any, because you have studied what this radical can do. Okay, it's one. You can decarboxylate, then you can see what radicals you are getting up. Then you have studied what it does. It can abstract an hydrogen. Acyl radical can abstract an hydrogen. If acyl radical abstracts an hydrogen, then what you get? You get an aldehyde in, right. If alkyl radical abstracts, then what you should get, but in this case you do not get that possibility, ketene, right. So, that all you have to now work on this and find out what are the products it can give, right. So, major product you get out of this is get this as a nice aldehyde type of system. Think of writing as a straight chain, then you will know. Right, looks like a simple molecule, and I am trying to do all the chemistry here. I have generated some different radicals from here. From here you can generate your 1,5 diradical also. So, when a molecule is given, you put your mind and see whether it undergoes all other chemistry. Now, you are studying only alpha cleavage reaction and beta cleavage reaction. In next class you will be studying hydrogen abstraction reactions, then you should know, because all this chemistry is done by your carbonyl only. So, your carbonyl can, then you should understand whether my carbonyl system will do alpha cleavage or beta cleavage, or it will do intramolecular hydrogen abstraction, what type of chemistry, or whether it will do all these things together, that also happens, okay. So, it becomes nice once you go for good examples, okay. Beta cleavage, there is a competition, but you can get beta cleavage as more products, both are fissile, okay. The products in this case beta cleavage products you get more, okay. Okay. Now, we will take simple example, let it be a little bit simple example, so that just to see whether you remember what we learned in 5 minutes before. Okay. So, what you do? So, shall I, once I shine light, I will say that I will go for S1, then I do intersystem crossing to T1, no, because it is a epoxy ketone, that is good. So, you remember then, now from S1 I can do my cleavage. So, in this case you know that I can cleave because the CO bond is little bit weak. So, I can get a radical, what radical I can get? I can get a phenyl, methyl, O dot, looks like a simple system. Now it is again a 1 2 3 1 3 diradical system. What you are preferring to do here? 1 3 diradical system. Hmm? Uh, so you want to shift your methyl. Why you are not shifting your phenyl? No, you have an option here, right? I can say that I am doing 1 3 1 2 methyl shift you are doing. I am asking why cannot you do 1 2 phenyl shift? Anything wrong? Yes. That is what you have to remember. If instead of my phenyl, if I have some other molecule, then you have to always, you should not think about moving only your methyl. Okay. It depends upon which undergoes a faster shift. In this case it is methyl. Okay. I cannot take my phenyl dot. Okay. It is very hard to generate that. Okay, so that is my product I get. So, with two basic ketones I am working on, one cyclopropane ketone, another I am working on epoxy ketone. We saw 1 2 hydrogen shift, we are now seeing 1 2 methyl shift. Okay. Normally you can call it as 1 2 alkyl shift, there are many cases where it happens. Okay. Fine. Now we will see another example where you are not doing your 1 2 methyl shift. Yes. In the previous example, you you want to break which this bond, but this is the weakest bond, na? No, see stability, but your bond also plays an important role. Why this energy transfer happens? Normally the energy transfer happens, then your weakest bond breaks. Okay. This side is not alpha beta. Okay, so energy transfer does not happen there. Okay. See, this you can see from your UV spectra. Normal ketones have, like, once in UV spectra you can see this epoxy as well as cyclopropane have influence on your carbonyl. You can see a shift in the spectrum. That is how you find out there is energy transfer taking place. That is good. Yeah, keep on thinking in that way, it is nothing wrong in it. Okay. So, I have a system now with an epoxy ketone like this. So, what it can do now? You say it is photolysis, it goes to S1. From my S1 I can get so I am getting a system where again I am getting 1 2 3 diradical, right, 1 2 3 diradical system. See, in 1 2 3 diradical system we have studied that you can nicely see your hydrogen shifting, we have studied methyl can shift. In this, can you think about which can shift? Yeah, you can see bond migration. Okay. I can migrate this bond, that bond migration happens. you call as rearrangement product or something, but bond migration nicely happens. So, write the structure. When you do this type of thing, just without seeing the board, write the structure. That will be more interesting. Write it by yourself without seeing the board. So, you are getting one ring expansion one side and you are getting a contraction in one side. So, you are getting a type of heptanone and pentanone system, and this reaction goes so nice, like it is very hard to do in other way. Just by shining light you get this product nicely, very good migration happens. Okay. Which bond?
The other one.
This one? The other one is?
No sir, the other no sir, the one which attached to that curve only.
This?
No sir, the other bond.
No, what bond you are talking about? This one?
No sir, in this ring.
In this ring?
Yes sir.
You want to
Yes sir. Yes sir.
move this bond?
Yes sir.
Here?
No sir, to that.
Yeah, I think one thing you are saying here, if this bond I can move, okay, it is a type of cyclohexanone where you have bicyclic system, where that bond you can always move. See, you have to draw like this, then you will understand, okay, rather than drawing as a cyclic. It never looks like cyclic system, then you will know how far that bond to move it up. Okay. Yeah, just what you do is that just draw moving this bond and see what product. See, always I am saying do not close your mind. Okay. These are the products we are getting. Okay. You do not close your mind. If you have any option, draw it, okay, and then show to me, and then we will discuss why it is not going. But initially itself do not say that no, okay. Draw the product. If you have any other options, draw it. Okay. Take another example. And once I shine light, I might end up with my S1, that is very clear. Then you have a chance of breaking your bond, right. What is your alpha? Have an alpha beta, right. So, you can break this bond, fine. So, you get a system K2 . You get like this. Now, write the product. Yeah, you get a, I can move this bond to the radical, this can happen. 6 member, above 6 member, right. See, these are the examples which you have to learn. You will see how different, see, just taking one example and doing a beta cleavage reaction is not. Beta cleavage reaction, you have to know like what radicals we are getting in. Then if it is, then you have to think about, if most of the time in beta cleavage you are getting only 1,3 diradicals. Then you think what are the options in 1,3 diradical, whether your hydrogen can be shifted or your methyl can be shifted or you can shift a bond. Okay. So, you are now left with 3 options, hydrogen shift or your methyl shift or your migration of bond whenever you do a beta cleavage reaction. Clean. Okay. Now, I will take an example. You guys think like what happens, like this is your famous example which you I think you have seen this structure. Just recover from, like recollect from your mind where you have seen this structure. You have seen this structure and you are going to deal with this structure in pericyclic reactions a lot. Okay. Right now we do not worry about that part, we will see our whether what chemistry is going to happen in this case. So, I have a system like this, okay. I have asked you to shine light. You think about all the chemistry whatever you learned, alpha, beta, 1,5, 1,4, 1,3 diradicals. See what you can think about and say that which will be the major product. Once I shine light, I get to my S1. Now, say whether it will undergo an intersystem crossing to give me T1 or it get me directly from S1, how the system looks like. It is like a ketone which is an alpha beta enone, okay, and you have a very strange type of ring. So, can I do some chemistry from S1 itself? Is possible. Okay. If I do from S1, then what chemistry I can look for? I can look for some beta cleavage, right, or alpha cleavage. In this case, can I look for an alpha cleavage? How you can think of looking an alpha cleavage reaction? I do not think. See, if I do an alpha, just do. If I do an alpha cleavage here, it is not facile, it is not going to happen. If I do an alpha cleavage here, again it is not going to happen, because I am putting a radical on a strained ring. So, that is not going to be possible. So, then I am left with a choice of beta cleavage. Okay. If it is beta cleavage, then I have a cyclopropane ring. I can break the cyclopropane here, okay. Options are there. I can break it here, where you want to preferably break. This I can write alpha beta, I can write this also alpha beta. Okay. So, I can call this A, I can call this B. Which ring you want to break? A, because you are making to be free, you get a cyclic ring. So, that is how you, it looks to be, once you know the idea, it looks to be simple. So, I will get a radical once I break this. So, So, what you are now trying to do, or you want to, it is a 1, 2, 3, you want to migrate a bond, hydrogen is also available. What this molecule?
Want to have methyl.
Yeah, you can do your methyl shift, nice. Okay. So, that is how you ask yourself and say that this is not possible, this is possible. So, I do a methyl shift then. So, this type of methyl shift, it is now you have to tell me like a stereochemistry, no? Where you can conserve your stereochemistry, or you are going to lose your stereochemistry of your methyl shift. Want to conserve. It goes in a concerted fashion. This all this. So, we studied about your pericyclic reaction. It does not go by it's a concerted fashion, or it's you know that we are studying this is a radical type of chemistry, right? It is not a concerted fashion. Once your radical comes in, it is not going to be a much more concerted, right. So, what happens then? Whenever you do, that is why when you do your triplet chemistry, you lose your stereospecificity, you get non-stereospecific product, but if you when you do with singlet, yes, you get a stereospecific reactions, right. Same, because triplet are more like a radical, clear. I think these are the some good beta cleavage compounds which can do beta cleavage nice, fine. So, in this class what we will do, we will finish up with beta cleavage. Now, we have finished our cleavage reactions, carbonyl cleavage reactions we have seen. We have seen completely alpha cleavage, we have seen beta cleavage. What I will do next class, I will give you some assignments on cleavage reactions, so that you work it on, okay, and give me the assignment. So, from next class we will start now hydrogen abstraction reactions, okay, clear. Thank you.